In this video, I'm going to show you how you can process masked CNN for nuclei segmentation. So we're going to use the model we trained in the previous video. And so we're going to open the running Jupyter notebook to actually process this model. So it's always the same thing. First, we load all the packages, the codes, and then we can define the parameters. So here, parameters are really simple. We have input directory, images we want to process, the classifier, the model we want to use, and the output directory where we want to put the output images. And there's one thing that we need to define, and that's a parameter you'll have to probably fine-tune depending on your application. It's the size the image is seen by the network. So if you remember, for training, we set up the maximum as 256. However, if we use 256, is not going to be optimal because we use that augmentation, and with a different operation applied during that augmentation, there's a cropping and there's also some zooming transformation. So we actually have images with nuclei that look bigger, and so that's going to change the way we want to define the maximum dimension. So here we're gonna maybe we can try for different scales. So let's first define the different parameters, and maybe if we want to test, we can use only one image. So what I'm gonna do, I'm gonna go back to my Explorer, and so in datasets nuclei we have test folder with all the images we want to process. So let me just create a test for size. I'm just going to put one image, because as you're going to see, if UNet was extremely fast, the same way training is longer with masked CNN, processing is longer too. So just to test this parameter, we might just consider one image, and then we'll apply this parameter to all the images. So let's consider the first one, for example. And let's say we're going to try several parameters. So I'm going to define a new folder, result 256, for example. Result 512. Result 768, and result 1024. So it's a bit misleading. It goes the other way around. When we define the maximum as 256, we're gonna extract bigger nuclei. Just think about it. It's like you resize your image. So if your image is resized smaller, then it's going to look bigger. So let me define. So the input directory is going to be test for size. The input classifier is going to be the one with that augmentation. So this won't change. And we're going to do it. So actually, I'm going to do a batch processing for the parameters. So I can define 4 different runnings. And so everything's going to be run. So if I go back here, let's test for size. And then with that augmentation, all right. and it's going to be the one 256. All right, 256 here. Then I'm going to use the same test size, same model, data augmentation, and this time I'm going to take the output 512. So that's the correct parameter again. So it's going to be test for size and data augmentation and 768. So I'm going to change it to 768. And finally, so this doesn't change. This doesn't change. And this time we're going to take 1024. So let me define it accordingly here. And now I have these 4 different runnings, so I can run it. All right. And I'm going to speed up the video so you don't have to wait for the entire time of processing. All right, it's done. So you can see here when when you run it, you have the name of the image that is processed, and you have the max dim parameter we change. So 1024, 768, 512, and at the beginning 256. So let's have a look at the results. And let's start with 256. So I'm going to open Fiji. I'm going to open each of these images and try to put them side by side so we can look at the different results. Even though here is just a segmentation, we'll use a annotator then. So this is for 256. This is for 512. So you see images that are processed by small images, 256 by 256. So that's why the intensity goes from there to there. But normally that should work fine at the borders between those times. So it should be okay. Now 768. And finally 124. So as you can see, those 2 last ones clearly are not optimal. We have less nuclei. If you look at these 2, you're going to see that here nuclei are smaller than here. So that's what I was saying at the beginning. The more you increase, the smaller the nuclei you're going to get. So here, clearly, the choice is going to be between those 2. So maybe we can open a annotator and look at the difference. By just looking quickly, all right, we see that we might have a higher density here. So probably 512 is better. Maybe it would be good to also look at other scales. It works similarly to different scales, actually. Ideally, you have one image that is annotated that was not used for the training, that you use. So then you can measure the accuracy with your different parameters, and you decide about the best parameter by looking at the accuracy. But it's not always easy to do that because you want to use as much annotated data as you have. So Something you can see here as well is that we have quite some nuclei in something that look like background. Let's adjust the contrast and push it a little bit. So here I push it a lot just to show you that, you know, this one, for example, might be real, but all these other ones, let me zoom in. You know, this maybe, but it's really faint. If I go back, you know, it's really faint. But clearly, you know, so these ones probably are real, but these ones aren't. So that's what we called hallucinations in deep learning. And this, by combining with UNet, we'll get rid of them. So don't worry about that. Something interesting is that when you look at the morphology, they really look real. MaskRCNN really does a better job than UNet about that, even though UNet already take into account the morphology. But here, as we directly try to identify individual nuclei, you know, it looks pretty good. And when you look at your result, it seems you make some errors, but most of the time the nuclei that you identify are correct, except the one you hallucinate. But you're just missing quite some. So that's what we have for 256. Let's now load the one with 512. And we'll just try quickly like this. So you see we have less hallucination, still some, but way less. And in this region particularly, it looks a little bit better. So we're gonna use this one. So I'm gonna process all of them with 512. Now, as you can see, we are still missing some regions. So let's zoom in this region, for example. Now here we are missing everything. So it's also because when you look, oops, so I added a nucleus, doesn't make a lot of sense. It's also because it's really hard to make a decision, and that's why MaskRCNN wasn't able here to make a decision. But that's why by combining with UNet, even though it won't be totally accurate, it should give an interesting result. So let's now process all the images, and in the next video I'll show you how you can combine results with MaskRCNN and results with UNet. So I'm gonna close this. I'm gonna go back here, and now as I decided I want 512, I'm gonna remove all of these guys. No, not this, sorry. So let's do that way. I'm gonna delete these guys. This one I'm gonna rename it as results, and I'm gonna I don't really have to do that because it would be erased by the next processing, but just to make things, I make sure I don't make any mistake. So now I'm going to process all the images in test with 512. So let's go back to the notebook. So I'm going to redefine the parameters because now I just want to do one running with one parameter. So this is still the same. Test. So we have 14 images we want to process. We use the one with data augmentation. And as an output, I'm going to use results folder. All right. And 512. And let's run it. So again, I'm going to spin up the video because it's going to take some time to process all the images. All right, it's down. So here you can see there's something that you might not expect, invalid prediction. This happens when you don't identify any nucleus in an image. But just to to remind you how it works, here we have very huge images, 1800, 1400, but the algorithm just processes them by 256 by 256. So if you have one part of the image, 256 by 256 image patch, where you don't have any nucleus, which happens when you're on the border of the polyps, for example. If you might not have any, in the in the big image you have nuclei, but you might have image patches without any nucleus, then you'll see this invalid prediction pop up. So that doesn't mean that it's wrong. Then you can just check the image. So let's see, just to make sure that we actually identified nuclei in this image. So if I go there, in results, that's going to be, so I guess it's going to be the 13,694,32, this one. So let's open it with Fiji. And you see, so we actually got nuclei almost everywhere, but we probably had small, so we are on the border, so I guess in that case I would have to check with the original image, but this is outside the polyp, so this is all hallucination. And so then, there must be one small image patch here with no nucleus, and that's why we had this warning. But everything is fine. Sometimes you might have weird things like this. So here, clearly, nucleus was identified as a very large part. Again, by combining with UNet, we'll get rid of those. So we'll see that in the next video.